Next, I'm going to build, turn this around, build the, put in the power 8-volt regulator, make sure that works, and I'll put in the mixer and the local oscillator there. And once we do that, we should be able to receive stuff on the air. So now I should be able to put 12 volts in here, or 11 point whatever the battery's at. And if I look on the VCC pin of U2, which is pin 8, so I just got to poke. Pin 8 is this one here. I should see 8 volts between that pin and pin 3 is ground. And once that's the case, then we'll do the surface mount. So, grab the multimeter. I'm gonna want these clippy leads. Well, switch back to the classic pokey ones. And let's see, I'm expecting something in the 8-volt range. Turn that on. Let's see, ground is pin 3. VCC is pin 8. We're reading 8.03 volts, 8.04. Perfect. That means it is working. We hooked it up the right way. No magic smoke. Now the tricky part is doing surface mount. So I think that's enough to get the mixer working. We can check that the local oscillator is working. I have the probe, it's a little hard to see, connected to C10, that output side of C10. And when we apply power, if we look at the scope, we will see oscillation, and hopefully you can read it, but right here, frequency 7.0 to 7.03, it's flickering back and forth, and we expect it to be 7023 megahertz about. So there we have it. Nice, not really a sine wave, but RF at the frequency we expect. Mixers are a pretty common component. You see them in just about every receiver. So try and give you a quick understanding how they work. In a block diagram, they usually have a symbol like that, and you'll have 3 ports, usually RF. This is the local oscillator, and IF, so radio frequency, intermediate frequency, and local oscillator. And the way it works, for receive, you put the RF and the LO both go in, and out you get the sum and the difference. So that would be RF plus LO and RF minus LO. So for example, in this 49er, we have RF at, let's say, is 7.0 to 3.5 megahertz. So someone's transmitting a little bit above our crystal frequency. The local oscillator, we'll say, is running right at the crystal frequency, is 7.023 megahertz. And so the output of the mixer, the IF port, you'll get the difference, which is just 500 hertz, and you'll get the sum, which is 14.0465 megahertz, which obviously we only want the 500 hertz since this is audio tone, and so this will then go to the audio frequency amplifier and then to the headphones, and this one just gets filtered away and we can just ignore it. Since this is a direct conversion receiver, the LO is running basically at RF frequency. If this was a super heterodyne transceiver, you would have some local oscillator at some other frequency, so the RF would mix with the LO down to IF, which might be, say, 2 megahertz, because you have a bunch of crystals for an IF filter, and then there'll be another mixer to mix the 2 megahertz down to audio frequency. It does work the other way. You can put IF and LO and get RF out, but since the local oscillator is running at RF, there's no need to do that. We can just take the LO and directly amplify it for the transmitter half. Since we have the entire receiver built, it is a good test for that. If we look, you can see the mixer chip is this little guy right here, and that does its stuff through the audio amplifier and out to the speaker. So now, if I transmit close to 7023, let's do .5, let's say, we should get a tone coming out, and we'll be able to see it on the scope. And as I tune around, we should hear the tone change. So if I transmit, we have so as much as you can tell there, we're receiving throughout the passband, and you tune up and the audio frequency changes, which is what we expect.